Hey guys, today we're going to be talking about the geometric derivative. I'm going to be deriving it again because last episode I just feel like my energy wasn't too great. But I'm going to talk about this again. Hopefully you'll be able to better understand this because it's a more advanced concept. It's like taking everything you know from calculus, throwing it out the window, but then keeping some of it because it's still relevant. Um, and then just throwing all the addition stuff out the window and then taking it into this geometric world, into this multiplicative world. But yeah, so I'm going to kind of briefly go over it. So the product integral, which we denote like this, of a function f, and I'm just going to leave it as f. Technically it's f of x to the dx power. I'm just going to say it's f to, actually, you know what, I'll just say f of x to the dx power. This is defined to be equal to e to the integral of the natural log of f of x dx, right? This is the normal integral we're all used to, so we're going to take e to that integral of ln of f of x, right? So, it's weird. But basically, yeah, so the geometric derivative, what we really want is something that's pi of f prime, but it's not exactly f prime because we're taking it's not the normal derivative, it's geometric derivative, so it's f star. It's typically f star of x, and I'm just going to leave it as f star to the dx power, right? This is going to just be equal to e to the integral of ln of f star dx, right? So I hope this makes sense. I just left out the x parts because it really doesn't matter. And if we focus too much on it, this video is going to be like an hour long and it's going to be super cluttered. But yeah, so this is what we want, right? And so what we want this to be equal to, which again is equivalent to this, is we want this to be equal to f, just f, right? We want them to basically cancel out, and technically there should be a constant of integration, constant of integration multiplied by f, because we're dealing with the geometric world, so it's not going to be just plus c, it's going to be a times c, so just bear that in mind. So yeah, let's actually begin. So really what we're focused on is this part. So this, we want it to be equal to this, but we're going to focus on this to derive our expression for f star. So all we gotta do is just undo all of these. So let's first take the natural log of both sides. We get ln of f star, right, dx is equal to ln of cf. Oops, I keep doing that with the f's. It's going to be ln of cf, right? So this, we'll just do ln of f star, doing nothing on this side. This is equal to ln c plus ln f, right? So c is just a constant, so ln c is also a constant. So when we take the derivative of both sides to get rid of this integral, we get ln of f star, right? This is equal to, let me make that clear, ln of f star is equal to this derivative of that goes away, it goes to 0. Derivative of ln f is going to be f prime over f, right? That's just how the derivative is defined, and yes, the normal derivative. The geometric derivative, we're just going to say it's e to both sides, so this is e to the f prime over f, right? And the c, again, just goes away. Now, this is the same conclusion I arrived to in the last video, and I just cut that part off. That's really annoying. Hold on, give me a second. Okay, so, yeah, so f star of x, I just wrote it out in full. This is defined to be equal to e to f prime over f, right? That follows from this, okay? So the thing that I kind of got tripped up last time with is this should be the absolute value of f technically, because we have to have a positive input here. So what's that going to do? So if instead, so we pretend our absolute value bars here, 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 actually this part got cut off too, so let me just, yeah, so the only thing that's going to change is this last part. So we have the integral of ln of f star dx is equal to ln c plus ln of the absolute value of f, right? So then when we take the derivative, we get ln of f star is equal to, this goes to 0. Now this part is what's the interesting part. What's the derivative of the natural log of the absolute value of f of x? So first off, we're going to have this 1 over absolute value of f, right? And then we take the derivative of the inside, right? This is just a chain rule. Take the derivative of absolute value of f. So I'm going to make a video about this in the future, at some point in the future, probably like 2 weeks from now. But the derivative of, just take my word for it now, the derivative of the absolute value of f of x, let me just put it out in full, f of x is equal to, what was it equal to? It's equal to the absolute value, no. It's equal to f of x over absolute value of f of x times f prime of x, right? So because the derivative of the absolute value of x is just x over absolute value of x, but since we have this f, then we have to obviously multiply by the derivative of f. So this is going to give us times f over absolute value of f times f prime, right? So you might be like, oh god, this is a weird formula. This is f times f prime over absolute value of f squared. Why is that different than that? Actually, and then once you do that, you actually would just take e to both sides. Okay, so you might be like, oh god, this is terrible. Because then what you do is you take f star equals e to the f times f prime over the absolute value of f squared, and that's like, ugh, that's awful. But you should know that, let's say, I'll just say g over absolute value of g is equal to absolute value of g over g. Now let's do a little mini proof. So we have g times g, so g squared equals absolute value of g squared. If you just multiply this on this side and that on that side, cross multiplying basically. So g squared is equal to, so you should see that this is true, and if you're not convinced, you can just take the square root of both sides, right? On this side, you're obviously just going to get absolute value of g back. And remember, absolute value of a square root, square root of a square is just equal to the absolute value of the inside. And this is obviously true. So this statement here is true, right? So this is good, because what we can do is structure this in a way that we don't need this whole thing, right? We can just say, I'll just put it on this line down here, we can structure this so that we have this 1 over absolute value of f times absolute value of f over f, right? I just flipped this because we said that we can, then times f prime. This and that cancel, so now we're left with f prime over f, and then we get back to that same conclusion. So that's okay. So that whole thing, you might be like, oh, yeah, you should put an absolute value there. Well, really, yeah, you can, but it's not going to matter too much. You're still going to get this conclusion in the end. Okay, so we have some time. Let's talk about some of the properties that the geometric derivative has. All right, so we're only going to check a few things, but first I want to check, so again, remember, I denote the derivative like this, d star. This is like the d over dx operator. This is my d star operator. D star of, we'll say, a times f, where f is a function of x. So if this is the first thing I want to see, so constant times f, right? Actually, yeah, I'll just say a. So again, this is going to be e to the f prime, to the derivative of this over itself, basically. So the derivative of this is just going to be f prime, right? Over af. I'm sorry, it's af prime over af, right? So a times the derivative of f over like itself here. And you can see that these a's are going to cancel, right? So we're left with e to the f prime over f. And that is precisely the derivative, the geometric derivative of f. So this is precisely that. Right, so this is actually really good, because it basically says, all right, well, we get rid of our a's, basically. So constants really don't matter out front. Okay, the next thing I want to check is f plus g. And it's pretty much just going to be the same thing as f minus g. You would just replace the f's with a plus sign. Let me make that f a little better. So this is going to be e to the derivative of this, which is just f prime plus g prime, over f plus g, right? Because we put this back in the bottom. Actually, let me put it as a reminder over here. D star of f is equal to e to the f prime over f, right? So the derivative of this thing is that, and the derivative, and then we put it over itself. And this actually, like, this doesn't really simplify to anything. I don't think so, at least. If you, like, I don't see any way to do, like, a conjugate or anything. So really, there isn't any way to actually do this. And that should kind of make sense, because we don't have, actually, I don't think you can see me when I'm over there, but we don't have an actual, like, this sum rule works in the additive derivative case, but it's not going to work in the geometric case. That should kind of make sense to you, because we're in a multiplicative world now. So yeah. Okay, next thing I want to do is the derivative of f times g. And this should be more promising because, I mean, we're working in the geometric world. So let's see, this is going to be e to the, so up top, on the top of the fraction in the exponent, we're going to have just this normal product rule. So we have f prime g plus g prime f over fg, because that's, again, we're just putting this on the bottom again. So we have fg on the bottom. So then we can actually just play around with this. So we can actually break this up. So we have e to the f prime g over fg, right? Plus g prime f over fg, right? So you can see that this, so we have an f prime, so this g and that g are going to cancel, and this f and that f are going to cancel. So we're left with e to the f prime over g, I'm sorry, f prime over f, no, and then up here we have the plus g prime over g. And then we can split this up, right? Because this is e to the f prime over f times e to the g prime over g, right? We can just split this up from here to here. That's one of the properties of exponents. And this is precisely the derivative of f, the geometric derivative of f, and this is the geometric derivative of g. So what we have here is d star of f times d star of g. This is a satisfying product rule. We have that the derivative of a product is equal to the product of the derivatives. That is really satisfying, and that should make sense, again, because we are in a multiplicative world. So yeah, this property should make sense. So now let's check the quotient rule. And again, what we want is something very similar. We want something that works the same way, and it in fact does. It does work the same way. But let's just make sure, right? So this is going to be equal to e. So now we got to use the quotient rule. And actually, let me we're going to need a lot of space for our exponents. Let me just say it's e, a huge e. And so we're going to need the quotient rule up top, right? The normal quotient rule. So that's going to be low d high. So low d high minus high d low over low squared. So this is the top of my fraction. And we're going to divide it by, actually, we might need to make this e even bigger, right? So, and we're going to divide that by simply just f over g, right? So this is my quotient rule. We're gonna simplify this massively in a second. We're just gonna make this e to the, we're gonna combine fractions to make them no longer these weird complex whatever fractions. So whenever we're dividing by a fraction, we just multiply by its reciprocal. So we have this g times f. So let me say g over f times the whole thing. So g f prime minus f g prime over g squared. And you can notice that one of these g's and this g are going to cancel out. So I'm just going to do that right now. So we have 1 over g here like that. Alright, so now all we do is we can actually just multiply this fg, we can actually distribute that. We can put this in the bottom, so we can have it like that, right? So we have the fg on the bottom. We can split these up again, so we have g prime f over fg minus fg prime over fg. And you can see that this f and that f are going to cancel, this f and that f are going to cancel. Oh wait. No, I'm sorry. This doesn't work like that because this is a gf prime. Yeah, gf prime over fg, right? This is what we have. So you can see that this g and that g are going to cancel and these two f's cancel. So we have e to the f prime over f. And then we can actually just straight away divide this by e to the g prime over g. Right? Let me make this e like that, right? So we have e to the f prime over f over e to the g prime over g based on our, since we're subtracting, it turns into division. And this is precisely d star of f divided by d star of g. And that is satisfying. So yeah, that's basically how that works. Let's see, are there any others that I want to do? I don't think there are any other rules that I want to go through. There could be. The chain rule is actually pretty boring. You can just work that out for yourself. I don't remember of any other rules. So yeah, I'll just leave it at that. But if you want to talk about some rules, then go ahead. I might make a video on the geometric integral rules, but actually, I don't even really need to because, if you just have this, if these two things are equal to each other, it makes things really easy because when you take the integral of a product, it's just the product of an integral in the geometric sense, right? The geometric integral, right? And we have a geometric quotient rule for integrals as well, which is really unheard of. Okay, so yeah, basically that's it for the video. Yeah, so I went through all geometric derivatives and their rules, so I hope you enjoyed. Thanks for watching, and I'll see you in the next video. Bye, guys.